So, we will continue with our lectures on model predictive control. So, in the last lecture I showed you how you formulate the control problem as an optimization problem, and I left with the question of where is the model in all of this. So, we will address that question here. Just to recap, we talked about an optimization formulation where I have an objective function which has two terms. The first term has to do with the error in the output when compared with the set point, and this is the term for the control effort that we take while we do this optimization or the control of these systems. Okay. So, that gives you the objective function definition. The decision variables are u, k, k plus 1 all the way up to k plus m minus 1, and the constraints are on u and delta u, and I said that this constraint, if you expand this, a way to write this would be to say u of k plus I less than equal to u upper less than equal to u lower, where I goes from 1 to m minus 1. So, this is a formal way in which you write these constraints. So, basically the idea is this constraint is generically written for u, but since at every time instant we are talking about the same control input. So, the variable that we have defined for uk plus 1, sorry, this is I equal to 0, uk plus 1 all the way up to uk plus m minus 1, all of them have to follow the same upper and lower bound. So, that is what is written here. When I is 0, this becomes uk, when I is 1, this becomes uk plus 1, when I is 2, this becomes uk plus 2, and when I is m minus 1, it becomes uk plus m minus 1. So, that is how this constraint is applied on every control move that we take. Similarly, the general constraint on delta u can also be expanded like this: delta ul less than equal to delta u k plus I less than equal to delta u upper, and again I equal to 0 all the way up to m minus 1. So, basically what this says is when I is 0, delta u k, which is the difference here, should be between the range, the difference here also should be between a range, the difference here should be between a range, and so on. So, this becomes let us say m minus 1 constraints here, then m constraints here and m constraints here. So, there are 2 m constraints that you have here. So, this is the standard optimization formulation that we talked about. Now, coming back to how are you going to relate the whys to use is a question that we have. Basically, now that we have thought about the whole controller itself as a discrete controller, the model predictive controller. So, this is a discrete block, whereas a true process is really a continuous process. However, what we are saying is we are going to basically take samples at different sampling times. So, first sample at time equal to 0, the second sample at Ts, 2 Ts, and so on. So, basically in a discrete in a continuous controller, I have this process which gave me y values, which I compared with a set point, right, and I sent it to a controller. So, this continuous variable value is going into a controller, whereas here the process is still continuous. And what we are saying is we are only looking at the values at discrete time intervals. So, 0 Ts, 2 Ts, 3 Ts, that is the sampling time is Ts. And in the continuous case, then the controller went back and said it is going to manipulate some u, and that is going to act on p. That basically said the u is acting at all times. So, I keep changing u continuously. Whereas, in this case what we are saying is the way we formulated the model predictive control problem, if you had seen in the last lecture, we basically looked at making the control moves only at those sampling times. So, the idea was if I was sitting at k, I will make a control move at k, then k plus 1, k plus 2 all the way up to k plus m minus 1. Okay. So, the control moves are also made at those sampling times, and the measurements also come in at the sampling times. However, since the process is continuous, we have done this before. If you go back and look at the lecture where I talked about solving continuous state space models, you will see that I would have got a solution like this, and then you can get y of t like this. So, this is simply a repeat of what we have seen before for a state space solution. So, you can go back to these lectures and then look at the solution to the state space models, and you will get this. And if we assume deviation variable x naught is 0, then basically what you are going to get is x t is this and y t is this. Now, since we are talking about the output directly, so we are focusing on this equation here. Now, if you notice what this equation says is that the y at any time is going to be this integral right here, and if you notice this tau goes from 0 to t. So, u tau, that means u 0 to u t, all the values of u are taken into account and they are somehow weighted by some function to get me an output value. So, this is a key insight that we are going to derive from this equation. So, let me repeat this. So, what this says is, if you look at this integral and if you think of kind of integration as a sum, then you will see, since tau goes from 0 to t, u tau, that it is going from 0 to t, this term, and every time if you think of this as a sum, u of 0 is multiplied by some number here, u of next u will be multiplied by some number here, and so on. So, if you think of this in a continuous fashion, every u is multiplied by some number, and then integration, if you think of this as a summation, then all of these effects are being added up to give you what the value of y of t is. Okay. So, this is an important idea to start thinking about. Now, from a model predictive control viewpoint, what we are saying is, we are saying that this output now I can directly write as a function of these inputs, right. So, basically remember the question we asked, if I have a model plan, control input plan, how would that relate to the actual output values, and that is related through a model like this. The only thing is, this model is in continuous domain, whereas what we are interested in is deriving a model in the discrete domain, because most of the formulation and the solution are all in the discrete domain. Now, let us think about this as a sum, and then let us look at these terms in little more detail. So, if you look at this here, right here, so if you look at this term here, so you see this term is a function of t minus tau, okay, and this t minus tau, whatever function that is multiplying u of tau as tau goes from 0 to t. So, in other words, just if we substitute values of tau as different. So, if I substitute tau equal to 0, then basically this is some function of t times u of 0, right. If I substitute tau equal to 1, I get some function t minus 1 u of 1, and if I substitute tau equal to t, I will get f of 0 u of t, right. So, if you think of this as a function multiplying u of tau, this is being done continuously in a regular continuous model, but just to understand this all of this can be done very formally mathematically, but in the first control class I am going to show you why and how we go from a continuous model to discrete model in a very simple manner, appealing to intuition. There is no hand waving here. One can actually show how this will come about with concepts such as zero order hold, and actually doing this integration and showing that this is actually the form that you will get, but that is a little too much for this course right here. So, I am simply going to say how this happens and give you an intuitive feel for how these discrete models are derived. So, basically where we are going is, from this continuous model we basically want to go to the discrete form. Okay. So, basically what this says is the following. It says, if let us say you are looking at this multiplication, I am calling this as the f. So, we are looking at f, which seems to take as argument t minus tau and then u of tau d tau, and clearly tau goes from 0 to t. So, let me repeat this. If I take tau is 0, I get f of let us say t at multiplied by some 0. If I take tau equal to 1, t minus 1, u of n 1, and if I take tau equal to t, I get f of 0 u of t. So, in other words, as this keeps increasing the argument, this keeps actually going down. So, in some sense if you think about what we are modeling, think of this as a simple sum, then what as you might want to think of this as an approximation if you want, but we can by appropriately choosing this f, which is a slightly modified version of this, we will get it as an exact expression, but we will not worry about that right now. So, basically what this says is, if I think of this as a summation, it says y of t will be some f of 0 times u of t plus some f of 1 times u of t minus 1 all the way up to f of t times u of 0. Okay. So, you can think of this basically as the whole thing, okay, including the CB if you want as f. You can bring the CB in and think of that as a combined form of f. So, now you see that we have something which we can interpret. What we are basically saying is, if I have made control moves starting from time t equal to 0, 1, 2, 3 all the way up to t, and I want to know what is the effect of all of these control moves on y of t, then basically every control move is weighted by some function, right, and that function is let us say in this case f of 0, f of 1 all the way up to f of t. So, every control move here has an effect on the output. So, whatever basically you have done in the past also has an effect on what is the current situation that you are in. Similarly, all the control moves that you have made in the past have an impact on the current output, and depending on how far in the past you have made that move, there is a corresponding weighting that goes with that. Okay. So, for example, you would expect that this weighting will be basically larger than this weighting, simply because this u of 0 is a control move I made quite a while in the past, and the effect of that or the residual effects of that you would expect to go down over a period of time. Very simply, again very intuitive conceptually, if I do some actions today and think about the effect of this actions 5 years down the line, I would expect the actions I took 1 day before the 5 years will have a lot more effect on the output of the 5 year than what I did today in general, right. So, as these systems keep dynamically changing, the most recent changes will have a higher impact than the changes that happened quite a while in the past. However, the current output is a collective sum of some weighted function of all the inputs that have been taken before. So, all the actions I take now will have some impact on what my future is, and the way I compute that in a discrete model is I take each action and then I multiply it by a weighting function, and if it is an action that has been taken long time back, then the weighting function for that input will be less when I think about the current output, and whatever I have done recently will have a much bigger impact. Okay. So, if you think about this in a discrete form, now we will go back to the discrete form. Let us say if I look at t equal to kTs, which I am going to simply write as k. So, if I look at k in a discrete form, so what I am going to say is that I am going to convert this f function that I talked about into h, okay, and this h is called the impulse response model, and we will describe that. Just I am slight change of notation. So, I am going to say h1, I will finish this and then explain this, h1 u1 h2 u k minus 2 all the way up to maybe we will call this as h gamma u of k minus gamma. So, what basically this says is the current output that I have is a function of all the input moves that have been made in the past, okay, that is number 1 here. So, all of these are input moves that are made in the past with respect to k, right, because this is k minus 1, k minus 2, k minus gamma and so on, right. So, the current input y of k is a function of current output y of k is a function of all the inputs that I have had in the past, and these inputs that I have had in the past have different weightings based on how recent the input is or how in the past the input is in general. So, you would typically expect that things that are recent will have more impact. In general, this need not always be the case, but anyway, just as far as this class is concerned, let us keep things simple and simply interpret this equation. So, the past moves are uk minus 1, uk minus 2, uk minus gamma, and in fact I will go all the way to u0. But in general, when we look at these discrete model forms, what we will say is there is some memory in the system, right. So, while I could say what I am today is a collective impact of everything that I have done from the time I was born, typically what I am today is largely dictated by what I have done in some recent past, and before that whatever happened, that effect would have been minimized. In other words, maybe what I am today is whatever decisions I have made in the last 2-3 years. So, there is some memory associated with it. So, if I am at yk, I can say the memory extends only up to gamma terms, not more than that. So, anything beyond that I will say the weighting is 0, because that has been forgotten in terms of what the current output is. Okay. So, there are many ideas that we are using here. Number one is a very intuitive idea that whatever is the current output will be a function of all the input moves that have been made in the past. That is the first idea, and because it is a linear system, typically if I make some moves and I see an effect of that move on the output, this will be additive. So, let us say the impact of every move, if I add them up, then I will get the integrated impact on the output. So, that is the second idea. So, output depends on all the previous control moves that I have made, and if I can think of the effect of each of these control moves, then I can write the output as a sum of the effect of all of these moves, because anyway that is what we have been doing for linear systems. This linear superposition works is the second idea. Now, the third idea is that the effect of each of these control moves that I have made can be captured by a weighting function. So, in this case the weighting function is h1, h2, h gamma and so on. So, if it is just one input passed, then the weighting corresponding to that is h1. If it is 2 inputs passed, then the weighting corresponding that is h2, and if it is gamma inputs passed, the weighting is h gamma. Okay. So, the individual effects are actually captured through the weight, and the collective effect is actually captured through the summation, and the summation is because of linear superposition. So, that is a basic idea. Then on top of it, we are saying we are going to assume that this h of gamma, as you keep going more and more into the past, at some times it is going to cut off. The memory is only up to gamma. Beyond this, whatever terms that are there, they are very close to 0, the weights are very close to 0. So, in other words, if I have one more term in the past here, that will have a weight, and this weight will be very small. So, at some point we are going to cut off this expression, which is to say, look, whatever is the current situation is the linear superposition of everything that has been done in the past, but there is a limited memory in the system. So, beyond a certain limit, whatever was done in the past do not affect the current situation. So, that is the idea of cutting this at gamma. So, this is the effect of each of the individual moves, and the addition is the combined effort, and beyond this I am cutting off because of memory. Okay. Beyond this there is no need to worry about this, because those have such small effect that when you are looking at yk, it is enough to look at these. Okay. Now, the interesting thing to note is, once we understand it this way, whether this is k or k plus 1, it does not matter, the same rule will follow, which I will show here. But before that, I just do not want you to think that we have done some hand waving and gone from a integration to summation. Actually, under certain conditions and under certain assumptions, you can show that even if you integrate this equation with continuous u, where the u is changed in a stepwise fashion, and then you actually do this integration, and then actually compute yk at those time samples, you can show that this and this will be exactly the same under certain conditions. Okay. So, that I can show using mathematics without any hand waving, but that is not really important as far as this class is concerned, because what we are really looking for is we are looking at trying to explain how this notion of model comes into the optimization formulation, so that model predictive control problems can be solved. So, that is our goal. So, we will just understand this intuitively, and intuitively the understanding is very simple. One last time, the output at the current time depends on all the previous inputs you made, and because of linear superposition, the individual effect of these input moves can be added up, and the individual effect of each move is computed by a weighting function. And this is where I appealed to intuition and said, if you think of this integration as summation, each of this has a weighting function here. That is what is being captured here. The last thing that I want to show is, if I have y of k, then it is h1 u of k minus 1 and so on. K is just a running variable. So, you can change k to k plus 1, in which case here also you have to do k plus 1. So, k plus 1 minus 1 will be k minus 1, and this will be k plus 1 minus gamma. Basically what this says is the same thing. So, because k is just a dummy running variable, you do not have to really worry about it. The same ideas work in both the equations. For example, this equation says what the current value at k depends on everything that is done in the past up to gamma. So, that would be the input I took at uk minus 1, uk minus 2, uk minus gamma. Similarly, the output at k plus 1 will be depending on all the past, right. But now for k minus 1 is past, but for k plus 1 k is past, and if I take terms up to k minus gamma here, I have to take terms up to k plus 1 minus gamma, that is it. So, the past gets moved 1 because the k has become k plus 1. That is the first idea. The second thing you want to look at is, when I do k, the immediate past input k minus 1 I weight by h1, right, and the next past input I weight by h2 and so on. And if you look at this equation, the same thing will happen. The immediate past input, which is uk in this case, because this is k plus 1, is being weighted by h1. The next past input, which is k minus 1 in this case, because this is k plus 1, is weighted by h2 and so on. So, everything is consistent except that the counter keeps increasing. So, at every point, so if I am here, I have to weight all the inputs till here. If I am here, I move this also 1, right. So, that is what is happening here. Now, you see that you have a model between output and the inputs in the past. So, this is the critical model that we were looking for to complete this idea of model predictive control. So, let us take some examples to show you how this will work. I actually showed you this was the expression that we had derived mathematically. Now, when you convert this to this h gamma, the coefficient form, actually mathematically you show that if you use this weighting, you will get an exact result. We will not get into that, but what I am more interested in showing is that as you compute this h1, h2, h3 and so on, as you keep going down computing more and more coefficients for the model from this continuous model, you will see the numbers keep decreasing. At some point you can say that beyond this number is very small, I am not going to take the impact of this. So, for example, here the first number is 4.13, and if we keep going down and I come to 0.03 and so on. So, you might say, okay, for my model predictive control implementation, I am going to stop here because I am going to assume these are very small numbers and these are basically things that I can ignore. If you do that, then basically what you are saying is the current output is being affected by the previous, this is k minus 1, k minus 2, k minus 3, k minus 4 and k minus 5. So, I am going to only retain 1, 2, 3, 4, 5 terms here is what we are saying here. Now, if you say no, I want to be more accurate, I want to come till here, you will retain 7 terms and so on. But this tells you that for typical systems where we had the state space models and I have taken some values for A, B, C and then actually shown the computations of H. How this formula is derived I have not told you, but I have just told you that if you were to compute this, it will keep going down. At some point the memory effect will kick in and these coefficients will become smaller and smaller. So, that adding them in the model does not give you any purchase. So, this is the basic idea of how you derive a discrete model and how you think about a discrete model, which we are going to use in a model predictive control framework. So, the last lecture which will be the next one on model predictive control. Now that we have looked at an optimization formulation, you have looked at how to model an output as a function of previous inputs in a discrete framework, which is derived directly from this continuous solution. We are going to put all of this together and then show you a formulation for MPC and show you how we can get the controller implemented using MPC. So, I will see you again in the next lecture. Thank you.